Okay, I'm going to do one last problem from the practice exam. And this one is a tricky one because this involves two objects that are moving. One has a constant speed, the other has a constant acceleration. So we'll see how we can figure this out algebraically. This is the challenge problem. And this is not the kind of problem that we worked through in class, but I would think that you'd be able to solve bits and pieces of this given a little bit more information. So in this problem, we have two objects. We have a physics student and we have another student. And they start in the same location where there's a physics textbook off the ground. The student, the other student, another student, immediately starts running with a constant velocity of 6.2 meters per second. And our physics student isn't moving yet, but accelerates at a rate of 2.75 meters per second squared. And the question is, how long does it take for these two students to catch up to each other? And how far will they have run when they met up? So what you could imagine is that our student who saw the physics book initially, the physics student, is going to start off not moving and go faster and faster and faster and faster over time. The other student is going to start off at a constant velocity, but eventually they'll end up in the same place. And the reason is because the physics student is speeding up and eventually he will be going fast enough that he will have caught up with the other student. So the questions that we're asking are how long and where will these two students be? Now, these are two different objects. They each have their own accelerations and velocities at any given time. But we have a couple of things that we can use to help solve the problem. The first is that we can put them on the same reference frame. So we'll say that position X is 0 is where they both start, and we'll say to the right is positive. And then if we set up our kinematic equations, I'm going to use blue for the physics student. So my physics student starts at position 0, don't know where they end up. The initial velocity, we're told, is 0. Don't know how fast he's going at the end. The acceleration is 2.75 meters per second squared, and the amount of time we don't know. And then the other student, I'll use red for, also starts at position 0. Don't know where they end up. Their initial velocity is 6.2 meters per second, as is their final velocity, because they're running at a constant velocity with a acceleration of 0. And we don't know how long it takes. But here's what we do know. We do know that when they catch up, they both will have the same position and they both will have been traveling for the same amount of time. So our x variables for each of these objects are going to be the same, and our time variables are going to be the same for the time period over which we're interested in, which is the period during which they run and end up in the same spot for just an instant. So this is where it gets interesting, is that we can use some variables. So the simplest way to approach this requires a couple of steps. I'm going to do it the simple way because that's going to be easier. We're just going to use the variable t to indicate time. We don't know how long that time is, but we're going to use two equations and two unknowns to solve this. So if I were to look at my physics student, we'll find that we now, if we pretend that we know the time, we now have enough information to say that his final position is going to be equal to his initial position plus his initial velocity times time plus his acceleration times time 1/2 his acceleration times time squared. His initial position is 0. His initial velocity is 0. So this student should have a final position of 1/2 times 2.75 t squared. Now, we don't know what t is, but we can still write that in. Meanwhile, our other student is also going to have a final position equal to his initial position plus initial velocity times time plus 1/2 his acceleration times time squared. His initial position is 0. His acceleration is 0. So this student is going to have a final position of 6.2 times t. And this is where we can set up an equation. We have two equations for x, both in terms of t. So whatever this value is equal to whatever this value is. So I could put those two equations together, set them equal to each other. And then algebraically, we would solve this. So 2.75 divided by 2 is 1.375. Did I do that right? 1.375 t squared. Hang on, I better check my work because I've been known to make math errors with my mental math. 2.75 divided by 2 is 1.375. Okay, and then we'll subtract 6.2t from both sides, and that equals 0. And those of you who don't remember how to solve this problem, you factor t out. So we get that t times 1.375t minus 6.2 equals 0. If the product of these two terms is 0, then either t is 0 or 1.375t minus 6.2 is 0. They are in the same place after 0 seconds have gone by. They're also going to be in the same place when 1.375t minus 6.2 equals 0. And that's going to be when t is equal to 6.2 divided by 1.375, which is about 4.5 seconds. So there's the answer to the first part of the problem. How long will it take? And now that we have t, we have a couple different equations that we can plug it into. I'm going to plug it into this one. X is equal to 6.2 times t, which is going to be 6.2 times 4.5. And that ends up being about, oops, I did that wrong. 6.2 times 4.5 is about 27.9, so about 28 meters. So there's our distance, there's our time, and that's a fancy pants problem, but it's kind of neat to see that we can use our basic kinematic equations and some logic to solve a problem like that.